one backup. I wasn't sure if the system would work today, so just in case I made some preparations, but I kind of hoped the system would be fixed, and it looked like it was fixed. But turns out it wasn't. And now we don't know what's gonna happen. So I need as much backup as possible. And this is what you pay for your money, right? All right. So Echo 360 recording my voice, just in case I've got slides recorded, and I am recording Zoom, I believe, and I'm sharing the screen. And well, the computer is not very powerful. It is what it is. We cannot change anything. So, let's start from a question. And I know you should see the screen, and also you should see a small window that shows you what camera sees. And I'm going to switch to camera now. So you can double click on that small screen. And question is, how would I see what you see? Participants 39. Hide video panel, I don't need it, right? Now, well, there's always hope. So you can see the question, but first I need to talk about what does it mean to be connected in series and I've got my phone. You can call me if you cannot see what I'm doing. I believe this should be fine. So we have a parallel plate capacitor, and what we want is to connect another one. And there are different ways to do that. Basically, it depends on which electrode we connect with which. And in this situation, what does in series means? In series means that you have a wire and you attach it to one electrode of one capacitor, and you attach it to another electrode of another capacitor in such a way that you know they will have opposite charges. Now, for that, of course, we should kind of figure out what could be happening if we would attach a battery. Well, we could attach a battery. And for that, we need extra wires. So now, well, I can read, it says a minus. So now I know that if I connect the battery to another capacitor, something will begin happening everywhere. Well, right now it is not connected yet, so nothing is happening. But at this very instant, the battery starts acting like a pump. What does it do? It makes electrons move from one plate onto another plate. And if this says a minus and this says a plus, I know that people who made this battery made it in such a way that this electrode that says a plus has a higher potential. This has a lower potential difference, has a name voltage, and potential difference between these two electrodes has to be equal to what? 6. How do I know? I can read. So now, what is happening? Well, this battery generates potential difference between these two plates. And if this is negative, it says minus, lower potential, it means electrons will be moving on this plate. But the battery does not create electrons. The battery makes them move away from this electrode. So this electrode now is losing electrons, and then the battery moves them through, and then they run and settle down somewhere here. Equilibrium is reached almost instantly. But what's happening now? All right. This plate now is negatively charged. So electrons on this plate starts acting on electrons on this plate. Electrons and electrons hate each other, so they repel those electrons, and those electrons now actually have a room to travel through the wire, because wire is a conductor. It conducts electrons, and those electrons run away and they settle down here. So this plate loses electrons, that means becomes positively charged. But this plate gains electrons, that means becomes negatively charged. And in the end, what we have? Two charged capacitors. A negative charge, a positive charge, a negative charge, a positive charge. And of course, in equilibrium, the magnitude, the absolute value of the charge on each plate is the same. Q, so Q minus Q, Q minus Q. And this is what we call capacitors connected in series. And I can add another one. Of course, in this case, I need to reconnect the battery, break the circuit, take it away. And how should I connect it? Well, again, connecting this is wrong. This electrode has to be connected to this one of this capacitor. So if I make this connection, now charge could be distributed, redistributed between these two plates. But again, now if I I'll just do it this way. If I connect the battery to this plate, what's happening again? Well, now again, this battery makes electrons move away from this plate on this. They repel electrons of this plate, they move over here, becomes positively charged, negatively charged. These electrons repel electrons of this plate, they move over here, positively charged, negatively charged, positively charged. And again, the absolute value of the magnitude of each charge will be the same. Otherwise, it wouldn't be in equilibrium. So Q, negative Q, Q, negative Q, Q, negative Q. And that's supposed to be the answer. So you can see the question. But first I need to talk about what does it mean to be connected in series and I've got my phone. You can call me if you cannot see what I'm doing. I believe this should be fine. So we have a parallel plate capacitor, and what we want is to connect another one. And there are different ways to do that. Basically, it depends on which electrode we connect with which. And in this situation, what does in series means? In series means that you have a wire and you attach it to one electrode of one capacitor, and you attach it to another electrode of another capacitor in such a way that you know they will have opposite charges. Now, for that, of course, we should kind of figure out what could be happening if we would attach a battery. Well, we could attach a battery. And for that, we need extra wires. So now, well, I can read, it says a minus. So now I know that if I connect the battery to another capacitor, something will begin happening everywhere. Well, right now it is not connected yet, so nothing is happening. But at this very instant, the battery starts acting like a pump. What does it do? It makes electrons move from one plate onto another plate. And if this says a minus and this says a plus, I know that people who made this battery made it in such a way that this electrode that says a plus has a higher potential. This has a lower potential difference, has a name voltage, and potential difference between these two electrodes has to be equal to what? 6. How do I know? I can read. So now, what is happening? Well, this battery generates potential difference between these two plates. And if this is negative, it says minus, lower potential, it means electrons will be moving on this plate. But the battery does not create electrons. The battery makes them move away from this electrode. So this electrode now is losing electrons, and then the battery moves them through, and then they run and settle down somewhere here. Equilibrium is reached almost instantly. But what's happening now? All right. This plate now is negatively charged. So electrons on this plate starts acting on electrons on this plate. Electrons and electrons hate each other, so they repel those electrons, and those electrons now actually have a room to travel through the wire, because wire is a conductor. It conducts electrons, and those electrons run away and they settle down here. So this plate loses electrons, that means becomes positively charged. But this plate gains electrons, that means becomes negatively charged. And in the end, what we have? Two charged capacitors. A negative charge, a positive charge, a negative charge, a positive charge. And of course, in equilibrium, the magnitude, the absolute value of the charge on each plate is the same. Q, so Q minus Q, Q minus Q. And this is what we call capacitors connected in series. And I can add another one. Of course, in this case, I need to reconnect the battery, break the circuit, take it away. And how should I connect it? Well, again, connecting this is wrong. This electrode has to be connected to this one of this capacitor. So if I make this connection, now charge could be distributed, redistributed between these two plates. But again, now if I I'll just do it this way. If I connect the battery to this plate, what's happening again? Well, now again, this battery makes electrons move away from this plate on this. They repel electrons of this plate, they move over here, becomes positively charged, negatively charged. These electrons repel electrons of this plate, they move over here, positively charged, negatively charged, positively charged. And again, the absolute value of the magnitude of each charge will be the same. Otherwise, it wouldn't be in equilibrium. So Q, negative Q, Q, negative Q, Q, negative Q. And that's supposed to be the answer. So now I'm going to switch back to the screen, and you can do the same, just to draw what is happening. So for every specific element, we have a symbol which we use when we draw it on a screen or on a paper. Of course, we could use words. We could say a capacitor number one. First of all, it takes a lot of place and a lot of time. So we don't do that. We use a symbol, has been invented, and everybody uses this symbol for a capacitor. And a symbol for capacitance of this capacitor is a letter C, well, C1. Then we've got another one, then we've got another one. C2, C3, and right now they all are neutral, so we have to connect the battery. A standard symbol for the battery is like this: one long and one short lines. The long line represents a positive electrode. The short represents a negative electrode. Still not connected, so we need to connect. We could use wires just directly. We don't really need a switch. I can just connect it. And now we know what's going to start happening. The battery starts acting like a pump. So electrons will be moved. So by this pump will be moved like this, settle down here. And this electrode becomes negatively charged, but this becomes positively charged. And then when equilibrium is reached, so this positive, negative, positive, negative. But again, as we know, a capacitor in general is neutral, right? But the charge is split between two plates, and this term, charge, doesn't mean the charge of a physical capacitor. It means the charge on the positive plate of the capacitor. And in that case, they all will be the same in equilibrium, when equilibrium is reached. Otherwise, they will keep moving. Now we can use this, so this is the answer. And now we can use this to ask a question. Okay, what if I don't want to use 3 different capacitors? What if I want to use 1? But I don't want to store a different charge. I want to store the exactly same charge. So the question is, what single capacitor can I use to replace these, maybe 2, maybe 3, maybe n capacitors? They all may have different capacitance, but as we know now, they all will store the same charge, Q1, Q2, Q3, which is just Q. And what I want to have one capacitor which would store exactly the same charge, if I would connect it to exactly the same battery. That's important. So this voltage or potential difference should be the same as well. This is what I'm looking for. This capacitor has a name, the equivalent, and capacitance of the equivalent capacitor has a name, the equivalent capacitance. That's what we're looking for. So we need to prove the equation at the bottom. How do we do that? Well, of course, we have to use the relationship between charge, capacitance, and voltage. Technically, delta V is final minus initial, and this is higher minus lower. So now we could write the same equation for each capacitor. But now we have to be very careful. Just to test that you can see and hear, please call me and tell me what did I do wrong. When I wrote this equation, Q equals C1 times delta V, I put magnitudes. So that's not a mistake, but I made a mistake. An important mistake, not mathematical, physical. So please, someone, call me and tell me what you think. Did anybody hear me? Please call me. Just say anything. We'll talk. I just signed. Hello.
Hi, so I can hear you, but I need a little help trying to answer your question.
Okay, so first of all, please tell me what you see.
So I see capacitors connected
You mean you can see the screen, correct?
I do see the screen on Zoom.
Okay. Now, did you see my demonstration?
Yes.
Good. All right. Thank you. Now, and do you see a little window which shows you what the camera sees right now?
On Zoom,
Yes.
the camera's still pointed to your demonstration.
Perfect. So please zoom it. Just double click on it.
Okay.
Let's switch from the screen to the camera for the moment, okay? So you see how I connected this battery. This battery is connected to this plate, and another electrode is connected to this plate. These plates do not belong to the same capacitor. These plates belong to different capacitors. So the voltage delta V, which I use, is the voltage provided by this battery. It is equal to potential difference between these electrodes, and it is applied to the whole system. So we say this is the voltage across the whole system. But I am writing an equation now only for the first capacitor. Can I use the voltage applied to the whole system when I'm calculating charge on the first capacitor or wherever? What do you think?
No, because if charge is constant, then voltage could not be constant.
Well, it is constant in a sense. It doesn't change with time, but it is different. This is supposed to be the voltage across only capacitor number 1, and I didn't do that yet, but now I did it, and I fixed the mistake. Okay?
I see. Okay.
But
So
now,
charge is constant, voltage is not.
the word constant is tricky. Everything is constant here. Capacitance is constant, voltage is constant, even charge is constant, because they do not change.
Okay, so if the charge on each capacitor, the magnitude of the charge on each capacitor is constant.
Is the same, what you should say, not constant. You should say the charge on each capacitor is the same.
Okay, so if the charge on each capacitor is the same, the voltage or the potential difference on each capacitor should not be the same.
Exactly. And now you can finish the equation number 2 and the equation number 3. Because for each capacitor, we should use their own potential difference, their own voltage. So these equations all have the same structure, but they all have the same voltage in general, the same charge, because we consider this experiment, but the voltage might be different and capacitance might be different. So we have 1, 2, 3, 4 equations, but we are not done yet. Now please tell me how, this is very important, how can we relate, too many, these 4 voltages, delta V1, delta V2, delta V3, and total delta V?
So my instinct would be to use the equation we have at the bottom and rewrite each C in terms of QC delta.
No, we don't know the equation at the bottom. We're deriving this equation. We want to prove it. The equation at the bottom is our goal, and we cannot use our goal until we have reached it. It's just a goal so far. We need to make a relationship, some kind of a connection between these 4 voltages based on something we know, common sense, definition, something else.
Can we use QC delta V but rewrite it in terms of QC?
All right, clearly you need a different slide. There is nothing else, only delta V, delta V1, delta V2, and delta V3.
The sum of delta V1, 2,
Thank you. That's exactly what we have to write down. So at this point, thank you very much. We arrived at what we wanted to, so I'm going to drop the call. Thank you. This is a very important statement which we must use every time for any elements connected in series. First of all, we have to apply a definition of, well, voltage. What is voltage? This is a higher minus lower. That's basically difference, potential difference. So this is what we call V plus, this is what we call V minus. But electric potential changes, it might change it. And here we may have a different potential. Again, potential, call it 1, potential, call it 2. And a very common misconception is when happening when people confuse electric potential and voltage. Voltage or potential difference is actual physical difference. So delta V1 by definition must be equal to actual physical difference between potential here and potential here. Delta V2 must be equal to the actual potential difference between what? Oh, not plus. Electric potential here minus electric potential here. And the delta V3 has to be equal to actual difference between two potentials, a difference. But now it should be potential here minus potential there. So all we had to do is apply 4 times the same definition. V plus minus V minus, V plus minus V1, V1 minus V2, V2 minus V minus. So now, if you add these, first, second, and third together, mathematical exercise, but it's very simple because you're adding and subtracting same terms here and here. And what you get in the end, delta V1, voltage 1 plus voltage 2 plus voltage, 3, literally equal to V plus minus V1 plus V1 minus V2 plus V2 minus V minus. What's left? V plus minus V minus, which is total voltage across all the system. And we didn't do any physics here except we used the definition. But now we can use a combination of these equations. Delta V1. Delta V1 equals Q over C1. Delta V2 equals same Q over C2. Delta V3 equals same Q over C3. And delta V equals the same Q over C equivalent. So if I add them up, I should get what? Well, let's write it down. Q over C1 plus Q over C2 plus Q over C3 has to be equal to Q over C equivalent. And because the charge is the same, because it's specific connection in series, we get that to calculate the equivalent capacitance, we have to do this specific mathematics. And now, finally, we've proved the equation at the bottom. The goal is achieved. And now, again, remember, every time when we need to solve a problem, we have to answer several questions. For example, what to do and why. When we need to solve a problem about about capacitors connected in series, we can now erase from our memory all the reasoning and just remember this equation. And we will use it soon. But first, this is not a Webassign question. Let's just think about it. I'm going to switch to the camera again because I was told it works. And you can think about it. So camera. I have to break it down and again in individual capacitors. Oops. And now what does in parallel mean? Well, this looks like parallel, but that's why people call it parallel. But physically it means that you have to connect electrodes with the same charge, positive, positive, negative, negative. Now these capacitors connected in parallel. I can connect a battery now. And again, plus, minus, so if I connect, I can do it like this. Nothing is happening yet. I have to connect the battery to two plates. Now, in a fraction of a millisecond, what do we have? Well, because this is a positive electrode, how do I know? I have eyes. So this battery now starts moving electrons away from these both plates on both these plates. And now the charge may be different because, well, in this situation, if I have identical plates, still I can make distance different, and that means capacitance is different, and that means they will store different charge. Only if I have exactly same configuration, same area, same distance, same dielectric, the charge will be the same because capacitance will be the same. But I can change the area, increase the area. In that case, this capacitor will gain more charge. So the charge will not be the same anymore. But the question for you, what will be the same? And the answer is, of course, now the voltage is the same. Because now the voltage is simply provided by the battery. This battery is connected to this capacitor. But these wires basically make second capacitor also connected to the battery directly. I could have done it differently. I could just connect it directly to this capacitor, or even like this. It doesn't matter. Because this wire makes basically this one large plate. I even could have done it like this. Oops. Just make one large capacitor with the same plates. So this is basically what does parallel mean. Okay, and you can see what should happen. Now we should have more capacitance than before. One capacitor, second capacitor in parallel basically makes one larger capacitor. And by the way, if we would connect capacitors in series, that kind of means that we basically make a distance longer. Then we put something inside, but doesn't matter. When we make distance larger, the capacitance should decrease. And I will show you that it actually works this way. So for capacitors connected in parallel, charge is not the same, but the voltage has to be the same, because the voltage is only related to that battery. So positive electrode, negative electrode, connecting one capacitor. And again, what is voltage? Potential difference. There is potential here, there is potential here, and I would say most people usually set the low potential just to 0, it's easier. But because the wire is connecting capacitor to this electrode, just makes this plate charge with the same potential, and this wire makes this plate charge with the same potential. The voltage here, potential difference, is equal to the voltage provided by the battery. Same. And I can connect a different capacitor. Let's say with the smaller plates, different capacitance, but it doesn't matter. If I connect it using ideal wires, well, I could do it this way, doesn't really matter, as long as I see connection. Now, this potential again equals to the original potential V plus, and this will be equal to original potential V minus. Voltage will be equal to the same difference. By definition of voltage, it is equal to potential difference. So, as you can see, again, we will have the same voltage. So, technically, we should have said delta V1 equals delta V, delta V2 equals delta V. Same. And now, of course, we need to use it to prove, again, this is our goal. But how do we do it? It's actually much simpler now. Because, well, first, what do we want to achieve? We want to find what should a single capacitor be used, yeah, in order to replace two or three or more capacitors connected in parallel. Well, they all have the same voltage. But they may have different charges. What does this word equivalent mean now? What does it mean? Well, it means that if we apply the same voltage, this single capacitor should store the same charge. Which charge? Well, of course, complete, total, the combination of both. One capacitor stores a certain charge, another, and we want to store exactly the same amount. This is what we want. This is our goal. And to achieve this goal, what do? Well, this charge is supposed to be equal to capacitance times voltage. This charge is supposed to be equal to capacitance times voltage, number one. And this charge is supposed to be equal to capacitance times voltage, number two. But because, well, I rewrite it one more time. The voltage is the same. So I can just write delta V everywhere, delta V everywhere. I can cancel it. It's not 2 anymore, just delta V. I can cancel it out, and we get this done. So for capacitors connected in parallel, the equivalent capacitance of a single capacitor that can be used to replace those has to be equal to just the sum of individual capacitances. It's difficult to say. And now, again, this is all we need to remember. Series, parallel. These are key words. And of course, we need to be able to recognize when it is in series, when it's in parallel. And only then we can use one equation or another. An example. 1, 2, 3. This is equal to 1 microfarad, 2 microfarads, 3 microfarads. I need to find out a capacitance of a single capacitor that could replace these three. So what do? Well, I read and I find the key information, and now I say, okay, I will use microfarads, 1 over 1 plus 1 over 2 plus 1 over 3. So we've got a common factor of 6, and we've got 6 plus 3 plus 2. 11/6. Done. And of course, no, someone in the room would say, no. Why? Because we didn't find what we need to find. We need to find the equivalent capacitance first. And we didn't. So far, we just found 1 over equivalent capacitance. But it's an easy fix. We can just flip it, and the equivalent capacitance will be equal to 6/11 microfarads. Now, we are done. Now, calculate the charge. Well, something is missing. What is missing here for this information? Yes? Yes? All right, try again. Yes?
We need the voltage on the battery that's attached to the series.
Absolutely. So since it's not given, we can set it to any number. Let's say 100 volts. Thank you. And now we can calculate, well, actually, charge and more individual voltages. So can I use this voltage to calculate the charge number 1? No. To calculate charge number 1, I have to use the voltage number 1. But what I know is that for this particular connection, they're all the same. That's what I know. That means I can just use this capacitor, equivalent capacitor now, and say it should be equal to equivalent capacitance times voltage. So it's going to be equal to 6/11 times 10 to the negative 6 times 100. And that's going to be coulombs. But I can move further actually now. Now I know that the same charge Q1, which is the same as Q, yes, also should be equal to capacitance 1 times voltage number 1. But in this equation now, I know the charge because I just got it. 6/11 times 10 to the negative 4 coulombs. And I know the capacitance because it's given 1 microfarad. And now this calculation tells me how to calculate the voltage number 1. And I can repeat this reasoning and calculate the voltage number 2. Because, again, the same charge, 6/11, should be equal to the new capacitance times the new voltage. And I could repeat the same calculation again, but I also could calculate the voltage number 3 by doing this. It now has to be equal to the total voltage minus number 1 and minus number 2. And of course, I could calculate the same voltage using this equation, and it's a good exercise to do it, and make sure that you get the same answers, because if by any reason you get different answers, that means you made a mistake somewhere. V is supposed to be the same. Well, now the same capacitors connected in parallel. We know how to draw this particular circuit schematic. A plus to a plus to a plus, a minus to a minus to a minus. Capacitance 1, capacitance 2, capacitance 3. And I want to replace all these with only one. And I know now that it should be just the sum. So 1 plus 2 plus 3, 6 microfarads. Next step, okay, let's say we've got a battery that provides 100 volts. Same battery, same capacitors. We just wired it up differently. What do we have to say now? Well, for this simplest circuit, of course, the equation says that charge should be equal to capacitance times voltage. So this charge will be equal to 6 microfarads times 100, which is 6 times 10 to the negative 4 coulombs. But this will not be equal to charge number 1, or charge number 2, or charge number 3. No. Well, what I know is charge number 1 plus charge number 2 plus charge number 3 will be equal to this charge. And I want to again point at the importance of letters and their meanings. You see, this letter C means coulombs, coulombs, capacitance, capacitance. When you write a letter, you need to know what it means. All right. And of course, I can write this equation for every capacitor. How can I use it? What? Someone should mute Zoom. Well, how can I use it? I know in this equation capacitance.
Okay, great, thank you. You too, bye.
And voltage, because voltage is the same. So that's going to be 1 times 10 to the negative 4 coulombs. Q2 will be equal to, well, technically I have to write delta V2, but I know it's going to be the same for all of them. And I've got 2 times 10 to the negative 4 coulombs. And I can calculate 3 as total minus first and second, which is, of course, 3 times 10 to the 4 coulombs. Well, question, finally. And I will wait and I will check your answers on the Webassign for this question. So lecture 7. The summary. This is question number 3. I've got 32 students who have answered this already. And as you can see, the distribution is kind of 50-50, which is not really good. So I'm going to wait a little bit longer, see which answer wins. Well, we've got 12 for answer number 1 and 15 for the answer number 3. A tight majority. Well, the answer number 3 is correct. Okay, let's go to camera. If I only had capacitors 1 and 2, 1 and 2, that would be in series, no doubt. Even if I would add just one wire like this, it wouldn't make any difference. Even if I would add just one plate like this, it still practically wouldn't make any difference. Still, if we would connect the battery to these two capacitors, the most of the charge would be here. So this charge and this charge would still have the same magnitude. And that is important for capacitors connected in series. But if I attach another plate and connect it to a system, in that case, some charge from this plate must go away, or from this plate must go away. And now these plates may not have the same charge anymore. And that means they just can't be said in series. But naturally, they are not in parallel. So it's a false choice. In reality, we have 3 choices. Number 1, in series. Number 2, in parallel. And number 3, neither. And we have to be very careful. Otherwise, we make a mistake. If you think it's in series, you tend to replace these 2 capacitors with 1. And this is just wrong. You make a mistake, it doesn't work. Well, now let's solve this actual problem. The voltage is 6 volts, like in my example, and we've got capacitors. If we need to solve this problem, and we know that C1 and C2 are not connected in any way, well, we have to check all other possible pairs. C1, C2, C1, C3, C2, C3. And for each pair, we have to make a statement. Is it in series, in parallel, or neither? In series, in parallel, or neither? In series, in parallel, or neither? I'm going to give you a minute and make a statement about each pair of capacitors. And then we'll compare our notes. This is an important part of the reasoning process. Probably the most important part of the reasoning process. What's happening here? What's happening here? Am I in the Zoom or not? Can you see me? Okay. Yes, you can. So let's compare our nodes. C1 and C2, as we said, neither. It doesn't require any thinking right now. C1 and C3. Well, here you can clearly see two capacitors connected. Yes, in parallel. C2, C3, again, neither. So there is only one possible step for us to use this pair of capacitors to reduce the number of capacitors. So we can replace C1 and C3 by one capacitor. I call it C13. But in order to make circuit identical, equivalent, I need to, what? In parallel means I need to use a capacitor with the capacitance that is equal to the sum of capacitance 1 and 3. What can I do now? Remember the eternal question. What can I do now? Now I can actually physically or mentally replace these two capacitors with only one that is equivalent. This is a specific act. That is what we need to do. And that specific action, replacement, leads to a new circuit. Now I have only one capacitor instead of two on the left, and I have a remaining capacitor C2 connected, of course, to the same battery. Well, what can I do now? Now I can see that these two capacitors, now I've got a new pair of capacitors, and these are in series. And what can I do now? Act. Now I can replace these two with one equivalent. I can call it 132. And to calculate the new capacitance, I now have to use a different equation. And of course, it's going to be connected to the same battery. Six volts. And now what do I do? Well, now I can move back. So I started from my original circuit, and I was simplifying this circuit until I get the easiest possible circuit in the whole world. It only has two elements, a battery and one capacitor. But now, starting from this, I can move back to my original circuit. First, I can calculate the charge Q132. Q132 should be equal to capacitance 132 times the voltage. And the voltage is equal to 6 volts here. That's original battery voltage. Okay, done. So now I move back to step by step, back to a previous circuit. So I know that when capacitors are connected in series, that's supposed to be the same charge. So Q13 or Q2 should be equal to each other and should be equal to 132. The voltage will be different. This is the voltage 13. This is the voltage 2. Although the voltage 13 plus the voltage 2 should be equal to 6 volts. So, all right. Now, from this circuit, what can I write? Q13 is equal to C13 times delta V13. And what do I know in this equation? I know the charge. And I know the capacitance. So I can calculate this voltage. And if I know this voltage, I can calculate second voltage, delta V2. For example, it has to be equal to 6 minus delta V13. Of course, I could do it differently, yeah, because Q2 also should be equal to, well, again, they all the same, Q132, Q132, and should be equal to capacitance times voltage. Moving back. So where are we? We're here. This is the voltage number 2, and now we know it. This is the charge number 2, and now we know it because it equals to the charge number 132. But these two charges, 1 and 3, not known yet, which is fine, because now we know this voltage as well. We have found it. This is delta 13. How did I find it? Well, I found it here. Delta 13 equals charge 132 over C13. Where did I get capacitance? Here. Where did I get charge? Here. Now we have to carry the final calculation. Q1 should be equal to C1 times delta 13, and Q3 has to be equal to C3 times delta 1, 3. Well, we can see again, I have it. All right, I'll do it here. We can see again that delta 1, 3 voltage across these 2 points plus delta 2 should be equal to 6 volts. And of course, Q1 plus Q3 should be equal to Q132 come on. Moving on to the next problem. You can finish calculations and calculations are not important. The strategy is important. Remember, I told you many times, at least in PY105, physics is all about strategies. To choose the right strategy, you need to be able to recognize a specific situation and apply definitions and laws related to that specific situation. So, would you use the Newton's second law to solve this problem? Would you? Okay, good. No, you wouldn't. What would you use? Well, you would have to use definition of capacitance, Q equals C times delta T. You could use definition of potential difference of voltage, but first you would have to figure out, do you see anything connected in parallel or in series? And again, how many pairs do you see here? Well, C1, C2, C1, C3, C2, C3. For each pair, you have only 3 options: series, parallel, neither. Series, parallel, neither. Series, parallel, neither. Okay, C1, C2. This is actually exactly like this. If I just remove these 2 capacitors out, it will not change the way they being connected. And that's what we call in series, okay? C1, C2, in series. C1, C3, that's what you should say. And what do you say? Survey says, at equation number 4, and we still have 8 minutes. So far, in parallel wins, and that's wrong. Yes?
Sorry, I'm a little confused. The diagram looks exactly like the one from question 3.
No, it's
where
not.
it said that.
If you look, well, this is where you should maybe have your notes, you know, and if you see a diagram, you have to copy. Do you have a copy of a previous diagram?
Yeah, and C1 and C2 and C3 look exactly the same.
No, they're not. So either you have a wrong copy or,
Oh, I see what happened.
see, little things, big difference. So they are not the same. And it's a very important situation. You have to be able to analyze every single element of a circuit, not just devices, but also connections. And there is a difference, because in a previous circuit, this was the connection, and you didn't have this wire. And now, it's different. You have it rewired. And Well, you have to use your imagination. You could imagine like your hands was moving wires, and your hand grabbed this wire and moved it over here, or grabbed it here and moved it over here. Remember that the whole pyramid of understanding is based on imagination. Well, so this would have been in parallel, but adding an extra capacitor changes the voltage. Now the voltage number 1 and the voltage number 3 will not be equal to each other anymore. If not equal, hence can't be parallel. So neither, as well as C2 and C3. Well, this voltage across the second capacitor also may be different from voltage number 1, but it is definitely different from the voltage number 3. Why? Because the voltage number 3 is measured here. It's from this point to this point. This is electric potential plus, this is electric potential minus. This is electric potential 1. So delta V3 equals V plus minus V minus, and that is actually 6 volts. But delta V1 equals V plus minus V1, and delta V2 equals V1 minus V minus. By definition of potential difference, it equals difference between potentials. And you can see why they are not the same. And if they have different voltages, they cannot be in parallel. Well, so the answer is neither. Now let's just solve this problem, because now we know the strategy. And I'm going to go even faster. So we saw that we had one specific connection in series, C1 and C2. Hence, I can replace these two capacitors, keep C3, but I can replace these two capacitors with C1 too. I made a mistake here. I realized it later and I fixed it at the end of this video. Actually, right now, I already can calculate lots of things. 6 volts, Q3, Q12, Q1, Q2. Because C1 and C2 are in series, the charge actually is the same for 1, 2, or 1, 2. And right now, I don't even have to actually make another simplification. I can and I will, but I don't have to, because I can use now the rule for capacitors in parallel, C equivalent. Another mistake in my mind, I switched the connections. Six volts. I can calculate this total charge Q, which equals C equivalent times 6 volts. But this charge also has to be equal to what? Q12 plus Q3. And I could calculate those before individually because Q3 should be equal to capacitance times 6 volts. And Q12 should be equal to, well, which capacitance? 12 times 6 volts. And of course, I can calculate, let's say, I don't know, voltage number 2. Because the same charge Q2, which is as this Q1 or Q12, also has to be equal to capacitance times voltage. So I can calculate delta V2. And of course, I can calculate delta V1 because it equals 6 minus delta V2. Done. Now let's switch to the camera. Of course, nowadays we have devices that can use, come on, devices that actually camera work. At least they have light. So we have devices that can measure capacitance. Well, I hope you see it on the camera as well. '26, 27. Now let's connect them in series. Of course, now I need to measure the capacitance of the whole system across the system. You see? Less, like 17, 18. By adding capacitors in series, we're decreasing total capacitance. Now, what's going to happen if we connect them in parallel? Well, of course, I could do just this first. Oh, 23, 24. And now I'm adding in parallel. Yeah, so these two plates should touch. See? 30 something. Of course, because when we're connecting capacitors in parallel, we're basically giving more room for a charge to be stored. And if we add more and more, we get more capacitance. But if we do something weird with it, in that case, we cannot predict what's going to happen. We just have to calculate everything using the strategy. And now you know how to do that. And now we are done. Thank you very much. And the lecture is over. Have a nice day. Stay healthy. Let's see what's going to happen tomorrow. All right. All right. So we need to solve this problem. Let's see. Well, so far, focus is fine. And what do we know? Well, we know that capacitors C1 and C2, neither in parallel nor in series. Capacitors C2 and C3 also neither in series nor in parallel, but capacitors C1 and C3, these two capacitors in parallel. So I can replace these two with one capacitor. Now, this is not the problem I want to solve. Because this problem was solved, right? This is the problem I want to solve. Okay. This is the wrong picture. So delete slide. This is what I want. Oh, exactly. What the? This is the wrong picture. All right. Now we're getting there. This is the right picture. And in this problem, what do we see? Well, C1, C2 are in series. And that's the only connection we see. For example, C1, C3, not in parallel, and of course not in series, and C2, C3, not in parallel, not in series, we know that. So this is what we need to do. We need to replace C1 and C2 with only one capacitor, C12. And because they are in series, C12 comes from this equation, or we can just, when we have just simple calculation to make, we can just do it at once. C1 plus C2, that's C12, 1 over 1 over 1 plus 1 over 2. So that gives me 2 over 3 microfarads, 2/3. Okay. Makes sense. It should be someone between 1 and 2. Now, actually less, yeah, than either. Or anyway, what do we do now? Now we can redraw the circuit. We still have the same capacitor C3, but now we have replaced 1 and 2 with only one capacitor, 1, 2. Still connected to the same battery. So still same voltage. And now, again, we know what to do. Technically, right now, I don't have to make it even simpler. I could. Now, C1, 2, 3, that one we can use to replace 1, 2, and 3 is just the sum because they are in parallel. So I can make this as simple as possible, even if I don't really need it. And I can calculate this charge right now. So it's going to be 1, 2, 3, 2 over 3 plus 3, which is 11/9 microfarads, right? So this charge Q should be equal to C123 times delta V, which is 11/9 times 10 to the negative 6 because it's micro times 6. So we can cancel 3 and 3. 22 over 3, about 7 microcoulombs. Okay, whatever it is. But of course, we could just go back to the second simplified circuit and do this. Q12 should be equal to C12 times delta V, and that gives C12 2/3 times 6 times 10 to the negative 6 for microfarads, so 4. Two over 2, just checking, 2 over 3, yeah. C12, 2 over 3. And Q3 should be equal to C3 times same delta V, which is C3 3 times 10 to the negative 6 times 6, 18, 10 to the negative 6 coulombs. What I'm missing? Because Q12 and Q3 should be equal to Q. Brain freeze. What am I missing? I have an extra 3. 18 plus 4, 22. One over 1 plus 1 over 2, 3 over 2, and we flip it 2 over 3. C12 is correct. 2 over 3. 2 over 3. This capacitance number 3, we have to add them up, plus 3. That's 3. That's 9 over 3, 9 plus 2. Oh, of course. You see, brain freeze. That's supposed to be 3. Why did it write 9? I don't know. Our brain always plays tricks on us. But you see, because we know that we can check ourselves. So that's supposed to be 3, not 9. And that's supposed to be 22, well, over 1, which is 22. So 4 plus 18 is 22. Check, check, fixed, correct. All right, and what are we looking for? Individual charges. So Q3, this is Q3. We have found 18 times 10 to the negative 6th And Q12, which is here, should be equal to Q1 and Q2. They are the same. So Q2, Q1 equal to this number 4 times 10 to the negative 6 coulombs, 4 times 10 to the negative 6 coulombs. Well, what else can we calculate? Well, individual voltage, for example, here, delta V1, delta V2. Well, Q1 equals C1 times delta V1. So delta V1 will be equal to Q1 over C1. For Q1, Q2, Q12, we've got this number 4 times 10 to the negative 6. And the capacitance is equal to 1 microfarad. So we get 4 volts, which is a good number. Now we can calculate this. Of course, we could use the same equation. Delta V2 equals Q2 over C2, but Q2, Q1 are the same. And this is 2 microfarads, so 4 over 2, 2 volts, 2 volts. But it also should be equal to 6 minus 4, 2 volts. As we know, delta V1 plus delta V2 together should give 6 volts. So again, everything is a good match. And this is how we should solve this problem. Now let's switch to the camera. Of course, nowadays we have devices that can use, devices that actually camera work. At least they have light. So we have devices that can measure capacitance. Well, I hope you see it on the camera as well. '26, 27. Now, let's connect them in series. Of course, now I need to measure the capacitance of the whole system across the system. You see? Less, like 17, 18. By adding capacitors in series, we're decreasing total capacitance. Now, what's going to happen if we connect them in parallel? Well, of course, I could do just this first. Oh, 23, 24, and now I'm adding in parallel. Yeah, so these two plates should touch. See, 30 something. Of course, because when we connecting capacitors in parallel, we basically giving more room for a charge to be stored. And if we add more and more, we get more capacitance. But if we do something weird with it, in that case, we cannot predict what's going to happen. We just have to calculate everything using the strategy. And now you know how to do that. And now we are done. Thank you very much. And the lecture is over. Have a nice day. Stay healthy. Let's see what's going to happen tomorrow. All right. Bye, everybody.